Hello there, and a very warm welcome back to Sleep Science Time. Thank you for choosing this quiet corner of the internet to wind down your day. This is your time now, a moment to settle in, get comfortable, and let the noise of the world fade into something softer, something gentler. Tonight we're embarking on a journey that's quite literally beneath your feet. We'll be exploring the story of Earth itself from its violent molten birth in a cloud of cosmic debris all the way through to the present moment, and then peering cautiously into its rather uncertain future. It's a tale that spans 4.5 billion years, involves several catastrophic collisions, at least 5 mass extinctions, and somehow still manages to end with you, sitting here, probably in your pajamas, listening to this. Before we begin, I'd love to know where you're joining me from tonight. Are you tucked up in bed in Tokyo at midnight, listening from a sofa in Sydney at dawn? Perhaps you're in Seattle pretending to work while it's still light outside. Drop a comment and let me know where you are and what time it is. There's something rather lovely about imagining this story rippling out across time zones, connecting quiet moments all over the world. And if you enjoy these gentle journeys through science, a like and a subscription would mean the world truly. It helps this little channel grow, and it lets me know you'd like more of these calm explorations. For those of you already here, thank you. Your presence in this small constellation of curious, sleepy minds is genuinely appreciated. Now a small disclaimer. My goal tonight is not to make this so riveting that you stay awake until sunrise. Sleep is, after all, the destination we're aiming for. But if you do find yourself still listening by the end, I hope you'll drift off with your mind quietly full of deep time, ancient oceans, and the strange, beautiful fact that you're made of recycled stardust on a planet that's still very much alive. Right then, shall we begin? There's something rather surprising about our beautiful life-sustaining planet. It began its existence as an absolute nightmare. No gentle creation here, no careful assembly. Earth's origin story is 4.5 billion years of cosmic violence, punctuated by the occasional truly catastrophic collision. If you could travel back to the very beginning, you wouldn't recognize anything. There was no blue marble hanging in space, no swirling white clouds, no continents waiting to be named. There was only chaos, a vast spinning cloud of gas and dust, hanging in the darkness where our solar system would eventually form. This cloud, called the solar nebula, was the leftover debris from previous generations of stars that had lived, died, and exploded, scattering their remains across space like the universe's most dramatic recycling program. Picture this, if you will. A cloud so large it could swallow 1,000 solar systems slowly collapsing under its own gravity. As it collapsed, it began to spin, faster and faster, like a cosmic ice skater pulling in their arms. Most of the material fell toward the center, where it would eventually ignite into our sun. But not everything made it. A fraction of that cloud, perhaps 1 or 2%, remained in a flat, swirling disk around the young star. And it's from this disk, this leftover scraps bin of stellar formation, that the planets would form. Now you might imagine planets assembling themselves in some orderly fashion, like IKEA furniture with very clear instructions. The reality was far messier. In the early solar system, the disk was a chaotic soup of dust grains, pebbles, and rocky fragments, all orbiting the newborn sun at slightly different speeds. When these particles collided, sometimes they stuck together through static electricity and gentle gravitational nudges. A dust grain became a pebble became a boulder became a small asteroid. These growing bodies, called planetesimals, were the building blocks of planets, and they were remarkably enthusiastic about smashing into one another. Over millions of years, the larger planetesimals swept up the smaller ones, growing bigger and bigger through a process that sounds almost polite when scientists call it accretion, but was in fact an extended period of high-speed demolition derby. Earth began as one of these planetesimals somewhere in the inner solar system where it was warm enough for rocky materials to condense, but not so close to the sun that everything vaporized. It grew slowly at first, a modest clump of rock and metal in a dangerous neighborhood. But as it grew larger, its gravity became stronger, and it began pulling in material from farther away. Growth accelerated. Collisions became more frequent, more violent. Here's something worth pondering for a moment. Every impact, every collision released tremendous energy. When a mountain-sized rock slams into a growing planet at tens of kilometers per second, that energy has to go somewhere. It turns into heat. Enormous, searing, planet-melting heat. Early Earth wasn't just warm, it was molten. A ball of liquid rock, glowing red-hot in the darkness, its surface a churning ocean of magma with no solid ground anywhere. There were no days and nights as we know them, no atmosphere to speak of, just wisps of vaporized rock and metal. If you could somehow stand on this proto-Earth, which you absolutely couldn't because you'd instantly vaporize, you'd see a hellish landscape lit by the dull glow of molten stone, occasionally brightening when another planetesimal screamed in from space and exploded on impact. And then, roughly 4.5 billion years ago, something genuinely catastrophic happened. A Mars-sized planetesimal, which scientists have rather dramatically named Theia, was on a collision course with Earth. This wasn't a glancing blow or a minor fender bender. This was a direct planet-shattering impact. When Theia struck, the energy released was beyond comprehension. A significant portion of Earth's mantle was blown into space. Theia itself was destroyed, its core merging with Earth's, its shattered remnants joining the debris cloud. For a brief, violent moment, Earth ceased to be a single body. It was a ring of vaporized rock and metal, glowing white-hot, spread across thousands of kilometers of space. But gravity, as always, had other ideas. Over time, perhaps only a few thousand years, that ring of debris began to clump together, and from it, something new emerged. The moon. Our moon, Earth's constant companion, was born from violence. It's made partly of Earth, and partly of the object that nearly destroyed it. In a sense, the moon is Earth's sibling, its scar, and its reminder of just how close we came to never existing at all. After the impact, Earth was left in an even worse state than before. The entire surface was molten. The planet glowed like a dim star. Any atmosphere that might have been forming was blasted away into space. It would take millions of years for the surface to cool enough to form the first fragile crust, a thin skin of solid rock floating on an ocean of magma. And yet, improbably beautifully, this was the beginning. From this violent, molten chaos, a planet would eventually emerge. One with oceans, continents, weather, and billions of years later, someone lying in bed wondering how on earth, quite literally, it all began. After the chaos of the Theia impact, Earth was left looking rather sorry for itself. The entire surface was molten. glowing dully in the darkness like an angry coal that refused to go out. The newborn moon hung in the sky, far closer than it is today, perhaps only 15,000 miles away, compared to the current 250,000. If you could have somehow observed this scene, you'd have seen two battered worlds, one large and one small, both glowing faintly, locked in a gravitational pull that would shape both their futures. But the universe has a rather useful habit of letting things cool down given enough time, and Earth had nothing but time. Over the next few million years, the surface slowly, gradually began to solidify. Heat radiated away into space. The churning ocean of magma developed a skin, thin patches of solid rock that would form, break apart, and reform as currents in the molten layer below shifted and cracked them open again. It was fragile, temporary, but it was a start, the first crust. This early crust wasn't anything like the ground beneath your feet today. It was dark, dense basalt, similar to what you'd find on the ocean floor now. It was constantly recycled, melting and reforming as the planet continued to shed its primordial heat. But with each passing millennium, the crust grew thicker, more stable, less prone to sudden catastrophic melting. And then something remarkable happened. Water arrived. Now, here's where Earth's story takes a genuinely mysterious turn, because we're still not entirely sure where all that water came from. This is one of the great unsolved puzzles in planetary science, and it's worth pondering for a moment, because the answer determines whether Earth was always destined to become a blue planet, or whether it was just extraordinarily lucky. The leading theory involves a rather unglamorous source: asteroids and comets. During a period called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago, the inner solar system was pelted by an absolutely staggering number of asteroids and comets. These weren't the planet-shattering behemoths of Earth's formation, but smaller bodies, many of them rich in water ice and organic molecules. Each impact delivered a tiny fraction of an ocean. But add up millions of impacts over hundreds of millions of years, and you start to accumulate rather a lot of water. There's also evidence that Earth's interior may have held water all along, locked up in minerals deep within the mantle. As the planet cooled and volcanic activity raged across the surface, this water could have been released through countless eruptions, steaming out of the rock and into the atmosphere. The truth is probably some combination of both. Water from space, water from within, all accumulating slowly over time. But however it arrived, once it did, everything changed. At first, the water couldn't remain liquid on the surface. The planet was still too hot. Rain would fall from thick, oppressive clouds only to immediately evaporate when it touched the ground, creating a dense, steamy atmosphere that would make even the most enthusiastic sauna devotee reconsider their life choices. But as the surface continued to cool, eventually, somewhere around 4 billion years ago, a raindrop touched the ground and didn't evaporate. And then another, and another. Can you picture it? The first rain in Earth's history falling on a dark, rocky surface that had never known liquid water. Steam rising in great billowing clouds, slowly, gradually. Pools forming in the low places. Puddles becoming ponds, ponds becoming lakes, lakes merging into vast, shallow seas. The first ocean wasn't a single event. It was a process taking perhaps millions of years. Water collected in the lowest basins dissolved minerals from the rock and became increasingly salty. The sky, once choked with thick clouds of steam and volcanic gases, began to clear. For the first time since its formation, Earth's surface became visible from space, a dark world with patches of grey rock and expanding areas of deep, murky water. These early oceans were nothing like the sparkling blue seas we know today. They were hot, acidic, and probably tinted green or brown from dissolved iron and other minerals. The atmosphere above them was toxic, a mixture of carbon dioxide, nitrogen, and water vapor with virtually no oxygen. If you tried to breathe it, you'd last about as long as you would in a chimney. But it was an ocean. Liquid water stable on the surface, covering perhaps a third of the planet. And liquid water, as it turns out, is rather good at something important: chemistry. In those warm, mineral-rich seas, molecules could dissolve, interact, and combine in ways they never could in solid rock or empty space. Energy from volcanic vents on the ocean floor, lightning in the thick atmosphere, and ultraviolet radiation from the young sun all provided the spark for increasingly complex chemical reactions. Amino acids formed, nucleotides assembled. Lipids created tiny bubbles that could trap other molecules inside. We're still millions of years away from anything we'd call life, but the stage was being set. Earth had cooled enough to hold on to water. It had an ocean. It had chemistry happening in that ocean. And it had time, vast stretches of geological time, for that chemistry to become increasingly interesting. The moon, meanwhile, was slowly drifting away. The same tidal forces that caused Earth's crust to flex and crack were gradually pushing the moon into a higher orbit. Days, which might have been only 5 or 6 hours long in the immediate aftermath of the Theia impact, were slowly lengthening as Earth's rotation gradually slowed. It's a strange and lovely thought, isn't it? That Earth's oceans, the very thing that would eventually make life possible, arrived through a combination of cosmic violence and patient geological processes. That water, the most ordinary substance you can imagine, is actually one of the rarest and most precious things in the solar system, and that our planet just happened to be in the right place, at the right temperature, with the right gravity to hold on to it. Without water, Earth would have remained a barren, rocky world like Mars or Mercury. With water, it became something else entirely, a world where the surface could evolve, where chemistry could flourish, and where, eventually, something genuinely extraordinary would emerge. But we're getting ahead of ourselves. For now, Earth was simply a cooling planet with a new ocean, a clearing sky, and all the time in the world to see what might happen next. For perhaps 500 million years, Earth's oceans remained sterile. Oh, they were chemically active, certainly. Minerals dissolved, molecules formed and broke apart, volcanic vents pumped heat and chemicals into the water. But there was nothing alive, no cells, no reproduction, no metabolism, just chemistry, endlessly cycling through the same basic reactions. And then, somewhere around 3.8 to 3.5 billion years ago, something genuinely extraordinary happened. Chemistry became biology. Non-living matter organized itself into something that could maintain itself, replicate and evolve. Life began. We don't know exactly how it happened. This is, rather frustratingly, one of the biggest gaps in our understanding of Earth's history. We can see evidence of very early life in ancient rocks, but the exact process by which non-living chemicals first assembled into living cells remains maddeningly unclear. It's a bit like finding a finished novel but missing the crucial chapter where the protagonist makes their defining choice. What we do know is that the earliest life was almost certainly simple. Single-celled organisms, probably similar to modern bacteria, living in some warm waters near volcanic vents or in shallow tidal pools. They were small, vulnerable, and utterly unremarkable to look at. But they had one crucial ability. They could make copies of themselves. This changed everything, because once you have something that can reproduce, you have evolution. Organisms that are slightly better at surviving will make more copies. Random mutations will occasionally produce new capabilities. Over vast stretches of time, life becomes increasingly complex and diverse. Not because it's trying to improve, but simply because natural selection is extraordinarily good at finding solutions to problems. For the first billion years or so, life remained microscopic and marine. Bacteria and archaea, the two domains of simple single-celled organisms, diversified into countless forms. Some learned to eat sulfur compounds, others metabolized iron or methane. They formed mats on the seafloor, built tiny mineral structures, and filled ecological niches we're still discovering today. But they were all doing something rather important. They were changing the planet. You see, life doesn't just exist on Earth, it actively reshapes it. And nowhere is this more dramatic than in what happened next. Around 2.4 billion years ago, a group of bacteria called cyanobacteria developed a remarkable new trick. They learned how to split water molecules using sunlight, releasing oxygen as a waste product. This process, which we now call photosynthesis, would eventually make complex life possible, but first, it nearly destroyed everything. The problem was that oxygen, for all its life-giving properties now, was originally a poison. Most early life had evolved in an oxygen-free world and had no defense against this highly reactive gas. When cyanobacteria began pumping oxygen into the oceans and atmosphere in enormous quantities, it triggered what scientists rather dramatically call the Great Oxygenation Event, or for those who appreciate a good catastrophe, the oxygen catastrophe. Picture what happened. For hundreds of millions of years, oxygen levels slowly rose. It first reacted with dissolved iron in the oceans, creating vast deposits of rust that settled to the seafloor. These banded iron formations are still visible today, layers of red and black rock that record the moment Earth's oceans turned from green to clear. Once all the iron was used up, oxygen began accumulating in the atmosphere. For the anaerobic organisms that dominated early Earth, this was an extinction event. Oxygen was toxic to them, destroying their cellular machinery. Many species vanished entirely. Others retreated to oxygen-free environments, the deep ocean, buried sediments, anywhere the deadly gas couldn't reach. Even today, these anaerobic organisms still exist, hiding in the places oxygen can't go, living fossils from a different world. But some organisms adapted. They developed ways to neutralize oxygen, and eventually some even learned to use it. Aerobic respiration, the process of using oxygen to extract energy from food, is remarkably efficient. It provides roughly 15 times more energy than anaerobic processes. Organisms that could use oxygen suddenly had access to vast amounts of power. They could grow larger, move faster, do more. The Great Oxygenation Event transformed Earth in other ways too. Oxygen reacted with methane in the atmosphere, a potent greenhouse gas that had been keeping the planet warm. As methane levels dropped, global temperatures plummeted. Earth entered what's called the Huronian glaciation, possibly the longest ice age in our planet's history. For perhaps 300 million years, vast ice sheets may have covered much of the planet, possibly even extending to the equator in a scenario scientists call Snowball Earth. It sounds bleak, doesn't it? Life's great innovation nearly freezing the planet solid. But life, as it tends to do, persisted. Volcanic activity continued, pumping carbon dioxide into the atmosphere. Eventually, enough greenhouse gas accumulated to warm the planet again. The ice retreated, and Earth emerged from its deep freeze with an oxygen-rich atmosphere and a new possibility: complex life. For the next billion years or so, life remained predominantly single-celled, but it was becoming more sophisticated. Cells grew larger. Some developed internal compartments, becoming what we call eukaryotic cells, the kind that make up all complex life today, including you. These cells could do things bacteria couldn't, storing information more efficiently, growing larger, eventually even cooperating to form multicellular organisms. There's something rather beautiful about this chapter of Earth's history. Life didn't just adapt to the planet, it remade the planet to suit itself. Those ancient cyanobacteria, just trying to survive in their own small way, inadvertently terraformed Earth, turning it from a world of methane and ammonia into one of oxygen and possibility. They created the atmosphere you're breathing right now, every lungful a gift from organisms that died billions of years before the first fish ever swam. And Earth, for its part, learned a lesson it would repeat many times over. Life and planet are not separate things. They shape each other, co-evolve, create feedback loops that neither could produce alone. Earth isn't just a rock with life on it. It's a living system, a partnership between geology and biology that's been running for 3.5 billion years. Not bad for something that started as simple bacteria in a warm pond. While life was busily inventing photosynthesis and accidentally poisoning itself, Earth's interior was up to something rather dramatic of its own. Because unlike every other rocky planet we know of in our solar system, Earth refused to sit still. Its surface moves, it shifts, it recycles itself. And this restlessness, it turns out, is one of the main reasons you're here listening to this. Let's go back to basics for a moment. When Earth first formed and cooled, its interior settled into layers like a badly made trifle. At the very centre sits a solid iron core, roughly the size of the moon, under such tremendous pressure that despite temperatures of 5,000 degrees Celsius, it simply cannot melt. Surrounding this is a liquid outer core, also iron, where the temperature is slightly cooler but the pressure is low enough for the metal to flow. This churning liquid iron is what generates Earth's magnetic field, an invisible shield that protects us from solar radiation and prevents our atmosphere from being slowly stripped away by the solar wind. Above the core sits the mantle, a thick layer of hot, dense rock that makes up most of Earth's volume. Now, the mantle isn't liquid exactly, it's solid rock. But over geological timescales, it behaves more like an extremely thick, slow-moving fluid, a bit like warm toffee. Heat from the core rises through the mantle in vast circular currents called convection cells, the same process that makes porridge bubble when you heat it, only taking millions of years instead of minutes. And finally, floating on top of this slow-moving mantle, we have the crust, thin, brittle, and broken into pieces. These pieces, called tectonic plates, are constantly moving, driven by those convection currents below. they drift across the surface at roughly the speed your fingernails grow, a few centimeters per year. It doesn't sound like much, but over millions of years, it's enough to completely rearrange the planet. This process, plate tectonics, is Earth's secret weapon, and as far as we can tell, we're the only planet in the solar system that still has it working properly. Mars is too small and cooled too quickly. Its interior solidified, and its surface became locked in place billions of years ago. Venus is large enough and hot enough inside, but its surface appears to be one solid shell with no moving plates, possibly because it lacks water to lubricate the system. Earth somehow got it just right. And plate tectonics does something extraordinary. It recycles the surface. Where plates pull apart, new crust forms as magma wells up from below, creating mid-ocean ridges. Where plates collide, one is often forced beneath the other in a process called subduction, diving back into the mantle where it melts and is eventually recycled back to the surface through volcanoes. It's a slow but relentless process that ensures no part of Earth's surface is permanent. The oldest ocean floor on Earth is only about 200 million years old, practically yesterday in geological terms. Everything older has been subducted, melted and recycled. Even the oldest continental rocks, which are more buoyant and harder to destroy, are only about 4 billion years old. Earth is constantly erasing its own history, rewriting its surface, starting fresh. This has profound implications. Plate tectonics regulates Earth's climate by cycling carbon dioxide in and out of the atmosphere. Volcanic eruptions release CO2, while weathering of rocks and subduction lock it away again. It's a thermostat that's kept Earth's temperature relatively stable for billions of years, preventing it from either freezing solid like Mars or turning into a runaway greenhouse like Venus. It also creates mountains. When two continental plates collide, neither can be subducted because they're both too buoyant. Instead, they crumple upward, forming vast mountain ranges. The Himalayas, for instance, are still rising today, pushed up by the collision between the Indian and Eurasian plates at a rate of about 5 millimeters per year. Mount Everest, the tallest mountain on Earth, is actively growing, though erosion roughly keeps pace with the uplift. And where plates pull apart or slide past each other, we get earthquakes, sudden releases of built-up tension as the crust shifts. These can be devastating for human populations, but they're also evidence of a living, active planet. A planet that hasn't finished cooling, hasn't finished changing, hasn't stopped moving. There's something rather extraordinary about this, don't you think? The ground beneath your feet, which feels so solid and permanent, is actually drifting. The continents have been scattered and reunited multiple times over Earth's history. About 300 million years ago, all the land masses were joined together in one massive supercontinent called Pangaea. Before that, there were other supercontinents with wonderfully geological names like Rodinia and Columbia. And after Pangaea broke apart, the pieces slowly drifted into the familiar shapes we see on maps today. But they're still moving. North America and Europe are drifting apart at about the same rate your hair grows. The Atlantic Ocean is getting wider. The Pacific is shrinking. Australia is heading north toward Asia. In another 250 million years or so, the continents will probably reunite again into a new supercontinent, possibly centered around the Antarctic. Future geologists, if any exist, will draw very different maps. This restlessness isn't just interesting geology, it's essential for life. Plate tectonics creates diverse environments, mountains, valleys, islands, coastlines. It brings nutrients from the deep earth to the surface. It creates new volcanic islands where evolution can experiment with isolation. It regulates the climate and prevents the planet from becoming uninhabitable. Without plate tectonics, Earth would be a very different place, possibly a dead place, a world where the surface stopped changing, where mountains eroded down to nothing and were never replaced, where carbon dioxide accumulated unchecked in the atmosphere, where the magnetic field eventually faded as the core cooled. Instead, we have a planet that, even after 4.5 billion years, is still geologically alive, still churning and shifting and renewing itself, a planet that's as restless and dynamic as the life it supports. And that's rather comforting in its own way. To know that the world beneath us is as alive in its slow geological fashion as the world above it. If Earth's history were a novel, this would be the chapter where things get properly dramatic. Because while the planet was busy moving continents around and regulating its climate, life was experiencing something rather less pleasant: extinction. Not just individual species dying out, which happens all the time, but catastrophic, planet-wide collapses that wiped out the majority of living things in geological eye blinks. Earth has experienced 5 major mass extinction events, moments when more than 75% of species vanished within a relatively short period. These weren't gradual declines, they were catastrophes, written in the fossil record as sudden absences, whole groups of organisms that simply disappear from the rocks. The first major extinction, the Ordovician Silurian, occurred about 445 million years ago. At this point, life was still predominantly marine. Fish were just beginning to evolve, and nothing had yet crawled onto land permanently. Then, rather suddenly, the climate cooled. Massive ice sheets spread across the southern supercontinent of Gondwana. Sea levels dropped dramatically as water became locked up in glaciers, destroying the shallow marine habitats where most life existed. About 85% of marine species vanished. When the Ice Age ended and seas rose again, there was a second pulse of extinction, as environments changed once more. Life recovered, as it always does, but it took millions of years. The late Devonian extinction, around 375 million years ago, was more prolonged, a series of extinction pulses over several million years. The causes are still debated, possibly related to changes in ocean oxygen levels, possibly triggered by the evolution of the first deep-rooted plants on land, which would have increased weathering and changed nutrient cycles in the oceans. Whatever the cause, about 75% of species disappeared, particularly affecting marine life and early fish. But these extinctions, devastating as they were, pale in comparison to what happened at the end of the Permian period, 252 million years ago. This event, known somewhat cheerfully as the Great Dying, was the closest life has ever come to complete annihilation. Roughly 96% of marine species and 70% of terrestrial vertebrate species went extinct. It took millions of years for ecosystems to recover, and when they did, they looked completely different. What caused such devastation? The evidence points to a perfect storm of catastrophes. Massive volcanic eruptions in what's now Siberia released enormous amounts of lava, covering an area the size of Europe. These eruptions also released vast quantities of carbon dioxide and other gases, triggering rapid global warming. Ocean temperatures rose, oxygen levels crashed, and the seas became acidic. On land, temperatures soared to levels barely compatible with life. It was, quite literally, a global meltdown. Life clung on in a few refuges, pockets of survivable habitat where conditions weren't quite so apocalyptic. And slowly, over the next 10 million years, it began to diversify again. The world that emerged from the Permian extinction was dominated by new groups. The age of amphibians was over. The age of reptiles and eventually dinosaurs had begun. Which brings us to the fourth major extinction, the Triassic-Jurassic, about 201 million years ago. Another bout of massive volcanism, this time associated with the breakup of the supercontinent Pangaea, released gases that warmed the planet and acidified the oceans. About 80% of species vanished, but this extinction also opened up ecological niches that dinosaurs rapidly filled, leading to their dominance for the next 135 million years. And then came the most famous extinction of all, the one that ended the Cretaceous period 66 million years ago. You know this one, the asteroid. A rock roughly 10 kilometers across, traveling at about 20 kilometers per second, struck what's now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs. It vaporized rock, created a crater 150 kilometers wide, and sent a massive shockwave around the planet. Debris was blasted into space, some of it escaping Earth entirely, some falling back as a rain of molten rock that ignited wildfires across entire continents. Within hours, the sky would have been dark with dust and soot. Temperatures plummeted in what's called an impact winter. Photosynthesis stopped. Food chains collapsed. About 75% of all species went extinct, including all non-avian dinosaurs. The great reptiles that had dominated Earth for over 100 million years vanished in, geologically speaking, an instant. There's something almost absurd about it, isn't it? An entire planetary ecosystem, millions of species, billions of individual animals, all gone because of a random rock that happened to cross Earth's orbit at the wrong moment. No warning, no gradual decline, just sudden, catastrophic bad luck. But here's the interesting bit. Mass extinctions, awful as they are, create opportunity. Each extinction reshuffles the deck, opening up ecological niches and allowing new groups to diversify. After the Permian extinction, dinosaurs rose to dominance. After the Cretaceous extinction, mammals did. If that asteroid had missed, we probably wouldn't exist. Mammals might have remained small, nocturnal creatures scurrying in the shadows of dinosaurs forever. Between these major catastrophes, Earth also experienced numerous smaller extinctions and several more snowball Earth events, where ice may have covered the entire planet for millions of years. Each time, life found a way through, sometimes barely, clinging on in a few isolated spots. But it survived, and each time the ice melted or the volcanoes quieted or the dust settled, life exploded back with renewed vigor, filling the empty world with new forms, new strategies, new experiments. Earth's history is punctuated by these moments of near-total destruction followed by remarkable recovery. It's a reminder that our planet, for all its beauty and stability now, has been through extraordinary upheaval. The ground you're standing on has been repeatedly frozen, baked, drowned, and set on fire. And yet here we are, descendants of the survivors, the species lucky or adaptable enough to make it through. Sleep is a kind of small extinction, isn't it? A daily dying of consciousness, a temporary letting go of awareness, and yet we wake again, renewed, ready to continue. Perhaps that's what Earth does on a grander scale. Falls dormant, recovers, begins again. Over and over for billions of years, refusing to stay down. For 99.9% of Earth's history, humans didn't exist. Our entire species, Homo sapiens, has only been around for about 300,000 years. That's roughly 0.007% of Earth's total age. If you compressed Earth's 4.5 billion year history into a single 24-hour day, humans would appear at about 11:58:43 p.m. We're the newest arrival at a very old party. And yet, in our brief time here, we've become a geological force. We've altered the atmosphere, changed the climate, moved more Earth than all the world's rivers combined, and left traces that will persist in the rock record for millions of years. Future geologists, if they exist, will be able to identify our era with remarkable precision, not from our bones or our buildings, but from the layer of plastic, concrete, radioactive isotopes and fossil fuel residue we're leaving behind. But let's start at the beginning, or at least our beginning. Humans evolved in Africa during a period of dramatic climate instability. Over the past few million years, Earth has been cycling in and out of ice ages, with massive ice sheets advancing and retreating across the northern continents, roughly every 100,000 years. These climate swings were driven by subtle changes in Earth's orbit, tiny wobbles and variations that altered how much sunlight different parts of the planet received. Our ancestors evolved during these unstable times, adapting to rapidly changing environments. We developed large brains, complex social structures, and an unusual talent for making tools and solving problems. For most of human history, we lived as hunter-gatherers, moving with the seasons, following game and plant resources, making relatively little lasting impact on the planet. Then, about 12,000 years ago, something changed. The most recent ice age ended. The climate warmed and stabilized into what we call the Holocene epoch, an unusually steady and gentle period that's persisted to the present day. And in this stable climate, humans invented agriculture. The discovery that you could plant seeds, 10 crops, and harvest food in one place, rather than constantly moving to find it, transformed human society. Permanent settlements appeared. Populations grew, civilizations emerged. Within a few thousand years, humans went from small, nomadic bands to complex societies with cities, writing, and specialized labor. But agriculture also meant we began changing the planet in noticeable ways. Forests were cleared for fields, rivers were diverted for irrigation, domesticated animals replaced wild ones. For the first time, humans were actively reshaping landscapes on a large scale, not just adapting to them. Still, for most of history, these changes were local. Earth, on the whole, continued much as it always had. Glacial cycles persisted, though humans only experienced the warm interglacial period. The climate remained relatively stable. The atmosphere's composition barely changed. From space, Earth would have looked much the same in the year 1700 as it did 10,000 years earlier. And then came the Industrial Revolution. In the late 1700s, humans discovered how to harness fossil fuels, first coal, then oil and natural gas, on an unprecedented scale. These fuels, formed from ancient plants and microorganisms that died millions of years ago, released energy that had been locked underground for geological ages. With this energy, we built machines, factories, cities, and a civilization of astonishing complexity and power. But burning fossil fuels also releases carbon dioxide, lots of it. And CO2, as we've seen earlier in Earth's history, is a greenhouse gas. It traps heat in the atmosphere. For most of human history, atmospheric carbon dioxide hovered around 280 parts per million. Today, it's over 420 parts per million and rising. We've increased it by more than 50% in just over 2 centuries. The result is predictable because we understand how Earth's climate system works. The planet is warming, glaciers are melting, sea levels are rising, weather patterns are changing, species are struggling to adapt. We're not just living on Earth anymore, we're changing it, faster than at almost any point in the planet's history outside of major catastrophes. Here's where Earth's story becomes genuinely uncertain, because for the first time, one species, us, has become powerful enough to alter the planet's trajectory. We're in what some scientists call the Anthropocene, the age of humans, a new geological epoch defined by human influence. The current moment is strange and unprecedented. We live in an interglacial period that should, based on orbital cycles, be heading slowly toward another ice age over the next few tens of thousands of years. But our greenhouse gas emissions are warming the planet so rapidly that we may have effectively cancelled the next ice age. We're experiencing the warmest temperatures Earth has seen in at least 125,000 years, possibly much longer. At the same time, we're the first species in Earth's history capable of understanding what we're doing. We can measure atmospheric CO2. We can model future climates. We can see the consequences of our actions decades in advance. We have the knowledge and, increasingly, the technology to change course if we choose to. So here we are, a species that's existed for barely a geological eye blink, living on a planet that's 4.5 billion years old, capable of altering its climate and ecosystems on a global scale. It's an extraordinary position to be in, both terrifying and awe-inspiring. We're no longer just passengers on spaceship Earth. We're affecting the controls whether we meant to or not. The Holocene, that stable, gentle climate that allowed human civilization to flourish, may be ending. What comes next depends, unusually, on choices made by one particular species over the next few decades. Earth will continue, of course. It's survived far worse than us. But what kind of Earth it becomes and whether it remains hospitable to human civilization is genuinely up in the air. There's something humbling about that, right? That after 4.5 billion years of Earth's story, we find ourselves not at the end, but at a strange pivot point. A moment where the planet's future is, for the first time ever, partially in the hands of creatures who evolved only yesterday, and who are still learning how to be responsible for a world they barely understand. So where does Earth go from here? It's a question that operates on 2 very different timescales. The immediate future, which depends largely on what humans do over the next few centuries, and the deep future, billions of years ahead, which depends on forces far beyond our control. Let's start with the near term, the next few hundred to few thousand years. If humans continue burning fossil fuels at current rates, Earth's climate will warm by several degrees Celsius over the coming century. Ice sheets in Greenland and Antarctica will melt, raising sea levels by meters. Coastal cities will flood. Weather patterns will shift, making some regions wetter and others drier. Ecosystems will struggle to adapt. Many species will go extinct, unable to migrate fast enough or find suitable habitat in a rapidly changing world. But this isn't inevitable. If we reduce emissions quickly enough, if we transition to renewable energy and find ways to remove carbon from the atmosphere, we could stabilize the climate at a warmer but manageable level. Earth would look different, certainly, more chaotic weather, less predictable seasons, altered ecosystems, but it would remain recognizably Earth. Human civilization could adapt, though not without difficulty and cost. The Holocene's unusual stability may be over, but that doesn't mean catastrophe is guaranteed. It means we're entering a period of faster change, one that will require wisdom, cooperation, and a willingness to act on what we know about how the planet works. Future generations will inherit whatever climate we leave them. That's both a responsibility and an opportunity. But zoom out further, tens of thousands of years, and human influence becomes less dominant. Even if we stopped all emissions tomorrow, Earth's climate would continue evolving according to deeper cycles. The Milankovitch cycles, those orbital wobbles that drive ice ages, will continue their slow rhythm. Without human interference, Earth would likely slide back into a glacial period within the next 10,000 to 50,000 years, ice sheets advancing once more across North America and Europe. However, the CO2 we've already added to the atmosphere may delay or prevent this. Some studies suggest we've added so much greenhouse gas that the next ice age could be postponed by 100,000 years or more. In an ironic twist, human activity might have accidentally saved us from the next freeze, though at the cost of warming the planet far more rapidly than nature would have done. Looking ahead hundreds of thousands to millions of years, Earth will continue its restless dance of moving continents. The Atlantic will keep widening, the Pacific will shrink. Eventually, perhaps 200 to 250 million years from now, the continents will collide again, forming a new supercontinent. Some models predict it will center around the North Pole, others around the equator or even Antarctica. Whatever its configuration, this future Pangaea will reshape Earth's climate, ocean currents, and ecosystems entirely. When continents merge into a supercontinent, the interior becomes extremely dry. There's less coastline, less moisture from the oceans, vast deserts in the center. Mountain ranges rise where continents collide, altering wind patterns. Life adapts, as it always does, but it looks very different from what we know today. And then, on even longer timescales, the sun enters the picture. Our sun, like all stars, is slowly brightening as it ages. Over the next billion years, it will become about 10% more luminous. That might not sound like much, but it will gradually warm Earth. Oceans will evaporate faster. More water vapor, itself a greenhouse gas, will enter the atmosphere, creating a runaway warming effect. Somewhere between 500 million and 1 billion years from now, Earth's surface will likely become too hot for most complex life. The oceans will boil away. The atmosphere will thicken with steam. Earth will begin to resemble Venus, our hellish sister planet with its crushing atmosphere and lead-melting temperatures. Any life that survives will be microbial, extremophils clinging to existence in whatever protected niches remain. But the story doesn't quite end there. The sun will continue evolving, eventually exhausting its hydrogen fuel. In about 5 billion years, it will swell into a red giant, its outer layers expanding to perhaps the orbit of Mars. Earth, if it still exists, will likely be engulfed. Even if it survives by spiraling outward as the sun loses mass, it will be a charred, lifeless cinder, its oceans long gone, its atmosphere stripped away, its surface baked sterile. When the sun finally sheds its outer layers and collapses into a white dwarf, a dense, slowly cooling ember, Earth may still be there, orbiting in the darkness. A frozen, dead world. All traces of life, of oceans, of the billions of years of evolution and change erased by the dying gasps of its parent star. It's a sobering end, isn't it? After everything, after all the beauty and complexity, all the life and struggle, Earth returns to silence. A cold rock circling a fading light in an increasingly empty universe. But here's the thing worth remembering. That end is billions of years away. An almost unimaginable span of time. In the meantime, Earth is very much alive. It's moving, changing, supporting an astonishing diversity of life, including one species currently capable of wondering about its future. Whatever happens in the next few centuries or millennia, whatever climate we create, whatever choices we make, Earth will continue. Perhaps not in a form we'd recognize, perhaps not in a way that's hospitable to us, but it will persist. And maybe that's the real lesson from Earth's long story, that the planet is neither fragile nor indestructible. It's resilient, adaptable, and utterly indifferent to any individual species' survival, including ours. It's been through ice ages and hothouse climates, asteroid impacts and massive volcanic eruptions, snowball freezes and oxygen catastrophes. It's survived them all, not unchanged, but continuing. We're lucky to live in this moment, this brief window where Earth is temperate, beautiful and rich with life. A world of blue oceans and green forests, of seasons and weather, of birds and trees and quiet mornings like this one. It won't last forever. Nothing does. But for now, it's here. And so are we, able to contemplate it, study it, and perhaps, if we're wise enough, care for it a little while longer. Sleep well, knowing that the ground beneath you has already lived through billions of years of change and will be here in some form long after we're gone. The story continues, with or without us. That's not frightening. It's just the way of things. And that brings our journey through Earth's history to a close. From a violent birth in a cloud of debris, through cooling and the arrival of water, the emergence of life and its transformation of the atmosphere, the restless shifting of continents, mass extinctions and recoveries, right up to the present moment where one curious species has become powerful enough to reshape the planet and uncertain enough to wonder what comes next. If you're still awake, thank you for staying with me through these billions of years. It's been quite a journey, hasn't it? From molten chaos to blue oceans, from lifeless rock to a world teeming with complexity. And here you are, a temporary arrangement of atoms that was once part of ancient stars, now conscious enough to contemplate its own origins on a planet that's still very much alive. I hope this story has brought you some peace, or at least some perspective. In a world that often feels overwhelming, there's something oddly comforting about deep time. Your worries, your deadlines, your daily concerns, they're all real and valid, but they're also incredibly brief against the backdrop of geological time. Earth has been through far worse than anything we're experiencing today, and it's still here, still turning, still beautiful. If you've enjoyed these gentle explorations through science, a like and subscription would mean the world. It helps this little channel grow and lets me know you'd like more of these calm journeys through the cosmos. And for those of you who've been here before, who keep coming back to these quiet moments, thank you. Your presence genuinely matters. For anyone still listening, I'll now leave you with some soft ambient sounds to help you drift off. If you've already fallen asleep, well, that's rather the point, isn't it? I hope you've had pleasant dreams of ancient oceans and moving continents, of time stretching out in all directions, of a planet that's older and stranger and more resilient than we can quite imagine. Until next time, sleep well, and remember, you're made of stardust on a living planet spinning through space at 30 kilometers per second, and somehow, against all odds, you're here to think about it. Good night.